let me give you some examples. So sometimes you're given the second fundamental theorem of calculus, and you would be given this, and you're asked to find dy by dx. Okay, so sometimes you would be asked to use the second fundamental theorem of calculus to find dy by dx of this thing here. So when you look at this, so really what you're asked to do here is to find dy by dx. What is dy by dx of this? Well, if you look at this, hang on. So let me just move it up here. So looking at this, bear with me. Let me just move it up here. Hang on. So looking at this, hang on. So looking at this, hang on. So looking at this is exactly the same as this. So if you think about it, if you're asked to find dy by dx, you're asked to find dy by dx. That's really you differentiating this. And then if you look at this, when you differentiate this, it gives you capital F prime. So pretty much, and if you look at this from A to x. So this is, if you look at this, it is exactly the same as this, and this in a way is exactly the same as this. So you trying to find out dy by dx is really you differentiating it with respect to x. So looking up here, it's really you differentiating this with respect to x. So if you want to find dy by dx, so this here is like dy by dx. This is dy by dx equals small f, well, equals the function itself evaluated at x. So hang on. So because this is exactly the same as this, if you want to know dy by dx, then basically just look at the function itself, evaluate it at x. So really this thing here, dy by dx here, is really the function itself evaluated at x. So really it becomes this, x squared plus 3. I know it's kind of silly, but it's just an exercise to really get you to realize that if you differentiate this, then just look at this evaluator x. Okay, let me give you another example. So yeah, so when given this, dy by dx will be this. Okay, so here's another example. So here find dy by dx. Remember our theorem is from a to x. Remember our theorem is from a to x. Our theorem was from a to x, but here we've got x to a. So you've got to use one of the properties where if you switch these two around, then you stick a minus in front of it. There's a property that says that you can do that. So when given this here, to find dy by dx of this, just realize that our theorem only works from a number down here to x. You see, it's the x that's moving about. It's the x that's moving about. It's the x that's moving about, and it should be on top. But here it's at the bottom. So well, to switch these two around, you need to stick a minus in front of it. So to evaluate this, dy by dx equals, well, the first thing to do is switch these two around and then stick a minus in front of it. Okay, so that will then take you to this. Okay, so hang on. So from here, switch the two around. So now x is on the top, and then we can just apply our usual theorem. Okay, so now differentiate this side. That will then give you this. Now differentiate the whole lot on this side. So basically, when you're here, differentiate equally to both sides. That will then take you to here. Okay. Now this is like a -1 here. So -1 is a constant. You can take it out. One of the properties allows you to do that. So take the minus out here, and then just concentrate on on evaluating this. Now evaluating this is us applying the second fundamental theorem of calculus. So that will then take you to this, because when you differentiate this here from whatever to x here, it will be just concentrate on the function itself and then evaluate it at x. So that will then take you to here, and then blah blah. It will dy by dx equals this. Okay.